Hi, I'm Lindsay.
And I'm Marshall. Welcome to Tumble, the show where we explore stories of science discovery.
Today, we're talking about the challenge of getting a telescope into space. The James Webb Space Telescope is too big to fit into a rocket, so NASA decided to fold it up.
Sounds like the biggest origami project in the universe.
Definitely. We'll find out how to fold a space telescope right after this. So, Marshall, I want you to imagine something.
All right. I'm ready.
So imagine that you've worked for years to build a one-of-a-kind, super powerful, super expensive telescope with the ability to see back in time to almost the Big Bang.
Wow. A time travel telescope. I'm imagining it.
All right, so now you take that telescope, put it on a rocket, set it on fire, and launch it into space.
Wait, I do what?
That's how the people working on the James Webb Space Telescope feel about shooting their telescope into space. Knicole Colón is a NASA astrophysicist who's been working on the science behind Webb for years.
I do think that's the scariest part for me once it launches, because it's going up on a rocket and it's like on fire.
I mean, I think getting anything off Earth is nerve-wracking, let alone super powerful time travel telescopes.
Yes. So picture that telescope launched into space. The rocket launcher falls away and the telescope begins to unfold itself like origami in reverse.
To me, that's just a mind-boggling thing. I just think it is going to blow our minds when it worked and everything is like, how did we do this?
That's Alphonso Stewart, Webb's lead deployment systems engineer. He's got the huge job of making sure the telescope unfolds and works in space.
Wow, I mean, I'd say my mind is also boggled. It's exciting and scary enough to launch a telescope into space, but to have to unfold in space? Why add that extra step?
Because the telescope is actually too big for the rocket.
It can't launch in its full form. It just won't fit in the rocket. So it has to launch folded up in the first place.
Wait. So how'd they do that? Why does it have to be so big, first of all? And then how do they fold it? I've never folded a telescope.
That's what we're going to find out. How Webb is both the world's greatest science and the world's greatest packaging and delivery challenge.
So the James Webb Space Telescope, it's really this giant telescope, the largest telescope that NASA has ever launched.
Webb gets most of its size from a sun shield that stretches out like a tennis court.
So if you imagine a tennis court in space, that is the kind of thing that will be protecting Webb from the heat of the sun to keep it cool.
So it'd be like the hottest round of intergalactic tennis anyone's ever played. I mean, people have played intergalactic tennis before, just cold.
The sun isn't the only thing that's hot on Webb. The telescope itself is designed to study infrared light, also known as heat energy.
All the heat we feel as human beings, it's really infrared wavelengths, infrared radiation, if you will.
Infrared? What's that?
It's a kind of invisible light wave, just like X-rays or gamma rays, that need special technology in order to see them. Infrared light can reveal a hidden universe by giving us the ability to see past space dust and detecting objects that don't shine so brightly.
That just allows the opportunity to study everything from distant galaxies to nearby asteroids, all at infrared wavelengths.
Infrared light also hangs around for a very, very long time, which means we can use it to see into the past, back to the very beginnings of the universe.
Whoa, that's amazing. So how does Webb do that?
Webb has a giant mirror, which collects and concentrates all that infrared light into the telescope.
There's 18 small mirrors that come together to act as one big mirror.
These 18 hexagonal mirrors are plated in gold and give Webb the look of a bee's honeycomb.
Oh, for giant space bees, which I'm sure we're going to encounter.
This mirror altogether is 7 times bigger than Hubble's mirror. It's what makes Webb so powerful.
Okay, so let me see if I've gotten this straight. So you need a giant mirror to see in the infrared, and then you need an even bigger sun shield to protect it from burning up.
Yes, those two big things are necessary for Webb to do what it's meant to do science-wise. But then you've got to put it on a rocket. Here's Alphonso.
Well, if you look over and see the rocket and say, wait a minute, how do we fit this big thing in the rocket? And say, okay, well, I have to fold it up. Well, how do you fold it up? What material do you fold it up?
Just love the idea of scientists being like, here's our awesome telescope, guys! And then the engineers pointing at the rocket and being like, that won't fit.
Exactly. While the rocket is only a short part of the telescope's life, it's a very, very important part of getting it into space.
Seems like at the moment we don't have another way to get up there.
Yeah. So the telescope had to be designed for the rocket.
The rocket, it's a sort of an aluminum tube, a very large aluminum tube with an explosive at the bottom, a controlled explosion at the bottom.
Okay, so the telescope has to fold into a kind of cylindrical shape to fit in the tube with an explosion at the bottom.
Yes, and it has to fold up even smaller than the size of the rocket to fit into the protective equipment inside called the fairing.
So you have to give yourself room not to hit the walls of the fairing because that would be bad.
Wait, why would you hit the walls of the fairing?
Well, rockets vibrate a lot as they launch into space.
So it'd be kind of like shaking a package full of plates and you just open it up and a bunch of broken pieces of telescope fall out.
Yeah, so the engineers are constantly measuring to make sure that the space telescope is the right size.
We don't want to find out when we put in James Webb you can't fit the fairing on. That'll be a bad day. So you always have to keep track of the math.
I feel like that would be more than a bad day. It'd be like way worse than getting a couch that doesn't fit through your door, which I have definitely done.
Absolutely. But managing to fit the telescope into the rocket isn't the only thing to consider.
You can have it fit, but if it's too heavy, it won't work. First of all, the rocket won't get up off the ground. It'll go up a little bit and then fall down, or it won't go as high as necessary. So it's not just size, but it's also mass.
Yeah, I feel like rockets falling down is maybe not that good either.
So there's a really important weight limit.
As we were going along and you start putting all these features on and you start adding up the weight, he's like, wait a minute, I'm too heavy. I have to redesign and use a different material. I have to remove some things. I have to pare some things down. I have to make it lighter.
Alphonso gave the example of Webb's tennis court-sized sun shields.
Let's be crazy. Let's say it was all metal. If I try to fold it all up all metal, first of all, it'll be too heavy, be too complex, and I may not be able to fold it up small enough to fit in the rocket.
Engineers had to look for a material that was light and could fold up. They found a material called aluminized kapton.
What's that? It sounds fancy.
Actually, it's similar to something that's not so fancy.
If you look in a potato chip bag, and you look on the inside, it's aluminum, but you look on the outside, it has the plastic graphic. Well, this is kind of the same thing. It's a kind of plastic with aluminum on one side and plastic and special coating on the other side.
So it's a giant potato chip bag. Just think of all the chips you could take to space in a bag like that.
So that's how you squeeze a space telescope into a rocket, with a potato chip bag. The next challenge is how to get the telescope working in space. If it has any problems, it's too far out for astronauts to fix it.
Oh, there's no fixing it? So how do they make sure it works if it's more than 1 million miles away?
You test, and test again.
This is a big part of Alphonso's job, testing to make sure that Webb works in space before it leaves Earth.
You know, if in a perfect world, you would build one, the first one, find out all the problems, and then build the second one, and you'd be okay. But we have to do both simultaneously. So we are going to find errors. We are going to find things that doesn't work. We fix them and keep going.
So once it's in space, there's no do-overs.
You know, that would make me really nervous.
It makes us all nervous. Hence, the due diligence in the way we test it. We handle it in a very methodical way.
Webb is built so that there's no one way to operate it. If something breaks, there's a workaround.
It's like saying you're sitting in a living room with 2 TVs. You turn on the first one, it doesn't work, push it to the side and turn on the other one. And if that doesn't work, then you go to your phone and you turn your phone on.
Yeah, so there's always another way to watch Netflix, but instead of Netflix, it's studying the stars.
Exactly. Once Webb is tested, folded up, and launched into space, it's time to set it up as it travels 1.5 million miles away from Earth. This part is called deployment.
The first thing what we deploy is the solar array. Now, the reason why you have to do that is because you need power.
Webb's solar array is a series of solar panels that charge its battery.
It's nice to have power, but if you can't communicate with the spacecraft, it's no good. So the second thing we do is to deploy the antenna. So now you have power, you can communicate.
The communication antenna allows Webb to send and receive messages from its team on Earth.
So now you kind of relax a little bit and say, okay, now what do I want to do?
And that's when the great unfolding begins.
The way it's folded and stowed, that's kind of dictate how we unfold it. So you're basically doing kind of the reverse of what you've done.
All of those folding pieces are controlled by devices called actuators that drive them to open.
So it's like a remote control telescope.
We send a command, we wait, we get confirmation, we stop, everyone says okay, then we go to the next one. So it's very slow, methodical process.
The whole time Webb is unfolding and getting set up, Alphonso is what's called on console. That's a fancy NASA word for being at the command center.
Wait, does he get to say things like, Houston, we have a problem?
My phrase is, I have a situation to be solved. That's my phrase. That's my go-to phrase. The problem just seems like, what do we do? No, we have a situation to be solved.
That's so great. No problems, just situations to be solved.
Exactly. And unlike in the movies, NASA engineers can take their time.
And you have to figure it out a solution. Or you say, well, I don't know the answer yet. Give me a minute, something like that.
So the telescope isn't life and death.
Yeah, it's just incredibly high stakes.
Just decades of work, billions of dollars, and the answers to all the biggest questions in the universe, like how did we come to be?
Exactly. The rewards are huge, both for doing amazing science and having solved one of the world's biggest engineering challenges.
So what part of that is Alphonso most excited for?
The first time I get data that says the solar array is deployed. Because I think without power, I can't do anything else.
So just completing that very first step.
Yeah, getting over the first hurdle. Then it's that giant potato chip tennis court sun shield.
Because I know how complicated that thing is. And just pulling out a giant potato chip bag, I'm just phrasing it that way, but in a very freezing environment, the extreme environment of space, to me, that's just a mind-boggling thing.
I mean, that's probably the greatest mission a potato chip bag has ever been on.
For sure. Seriously, this telescope and its launch are pushing the limits of what humans can do and what we can learn. So to combat the mind-boggliness of the whole thing, NASA put together video animations to help people see how it's going to work. But Alphonso said those videos barely do justice to the true complexity of the project.
It's one thing to see the animations, in the media, but you don't see the hundreds and hundreds of little nuts, bolt, washer, pulleys, cables, springs, magnets, so many things. And to have all of that work in concert, just in an orchestrated way, it's just amazing.
When it does work, all those tests will be worth it.
In my mind, it's just a confirmation of all the work and the time that we put into the system. So yeah, it'll be cool.
I feel like saying it's going to be cool is a little bit of an understatement. There aren't really words to describe that magnitude of cool. It's like cool-tillion, cool-yillion, cool-golplex.
It's going to be something. So keep your eyes on Webb in the coming months and years. It's going to be showing us some pretty incredible stuff about the universe and our ability to explore it.
We've learned that a space telescope takes a huge effort by thousands of people to fold up into a small package. But there's lots of aerospace engineering you can fold on your own with just a piece of paper.
Start with a paper airplane. Can you figure out how to fold it to make it fly faster, go higher, or shoot straighter?
Test out your designs with friends and family and hold competitions to decide on the best design. We love making paper airplanes, so send us your designs at tumblepodcast@gmail.com. We'd love to see them.
Thanks today to Alphonso Stewart, James Webb Space Telescope Lead Deployment System Engineer, and Dr. Knicole Colón, Deputy Project Scientist for Exoplanet Science on James Webb. Special thanks to the folks at NASA, Dr. Amber Strawn and Elizabeth Landau, for helping us arrange these interviews.
Want to learn more about James Webb Space Telescope? We have so many resources on our website. You can watch animations of Webb deploying in space, learn more about infrared light, and see photos of Webb at the launch site.
Learn more about what Webb can show us about other planets in our bonus interview episode with Knicole Colón. Available to patrons who pledge $1 or more at patreon.com/Tumble Podcast.
Sarah Robertson-Lentz designed the episode art and is our head of partnerships. Eric Kuhn provided engineering and mixing.
I'm Lindsay Patterson, and I wrote and produced this episode.
And I'm Marshall Escamilla, and I made all of the music. Tumble is a production of Tumble Media. Thanks for listening, and stay tuned for more stories of science discovery.